you're probably going to have a hard time being wrong if you really understand these concepts carefully. So, my lecture today, it's mostly not really got to do with quantum mechanics also. It's really actually got to do with information theory and physical theory, information processing and physical theories in general, right? So I want to just inculcate this thought into your minds that physical theories are systems of information processing, right? This is, could you just move on to the next slide, please? Alright, so I presented these like key questions here that we're going to look at in this lecture, right? So, what is computing and how is it related to physics, right? So, if you read Nielsen Schon's great book on quantum information theory, he specifically says that the new paradigm in computing is that we've understood that physical theories are information processing platforms, basically. And what does he mean by that? So during JEE preparation, you guys probably made some circuits, some LCR circuits, and you realize how they're analogous to like a damped oscillator mechanical system, right? So if I ask you that I want you to plot a graph of what the position over time would look like for a damped oscillator, and you didn't really know how to solve the differential equation, what you could do is you could create the circuit and obtain the graph given to you, right? So that's what's called analog computation. But in general, the important thing to see here is that the physics is doing the calculation for you, for the universe to follow the math. That means the math is happening, right? So if you want to do particular calculations, if you want to solve differential equations, it's like analog computing. It's been known for a long time, people do this, but that's kind of the reason why quantum computing, like that's the way people approach quantum computing, right? So what is quantum computing or information theory, and how is it different from the theories that we studied before, classical theories, right? So quantum computing and information theory are, so computing and information theory are just general things, and they are just, computing is data processing, really. Computing is just data processing. So they are just systems of logic in which you manipulate data, right? You manipulate data. If you want to multiply it, that means you're going to take two pieces of data, you're going to do the corresponding operation. And the example is that real numbers are going to be, or it makes sense. There's a meaning of multiplying two numbers and getting another number, right? So it's just a system of logic. Computing and information theory just describes a system of logic, and quantum computing and information theory is just the system of logic that resides in this quantum structure of Hilbert spaces and of density matrices and of state vectors and whatnot, right? So it's just a logical system that exists in that mathematical framework that we call quantum mechanics. And that's what quantum computing is, and that's how it's different from classical mechanics. Alright? So what is the quantum advantage? So the quantum advantage is basically the fact that for the most part we can show that you can generate any classical result using a quantum system, but it's not the other way around, which means there are quantum systems that you simply, no matter what you do, you simply cannot simulate them using classical mechanics. Even if you add the hidden variables, which is what, if some people know, is Einstein's argument for EPR. But the entire point is that quantum mechanics and classical predictions are completely, they are not consistent. And we can test this, right? So that is the quantum advantage. And it manifests itself in algorithms in terms of like an order complexity advantage. But really it's just the fact that the logical structure is much richer and it allows you to do more things. Alright? So what is information and how does one formalize the notion of gaining information? Right? And I'm actually not going to speak too much on this point. I'm just going to bring up this question, but this will be addressed later. Alright? So is there a more fundamental construction of QM that one with informational principles? So this is the last topic I'm actually going to speak about. And for the few of you who have taken a quantum mechanics course so far, I'm sure you've been kind of perplexed when it starts off with a list of 5 arbitrary rules about density matrices or state vectors and the rule about measurements. And really, if you think about it, they're all ad hoc, they're arbitrary. We really can't justify them using nice logical fundamental means. They're just mathematical statements that work, right? But there's been a push in physics over the last 20 to 30 years to move away from that sort of description of quantum mechanics and to go to a more fundamental construction where the axioms are more, they're motivated in more base level logical principles. Alright? So, can you just go to the next slide? So, over here, I'm actually going to state 3, not exactly 3 of the assumptions of quantum mechanics research on this topic. That physical theories can be derived from base level informational principles. So I'm going to derive some of quantum mechanics postulates. I'm going to explain some of them using some base level informational principles, and some of them are the research has not yet found out. So it's not complete, this description. People are trying to develop it, but the simpler parts of it here I'll present for you today. So why do we need density matrices and how are they different from state vectors, right? So for the people who've done quantum mechanics, they know what these two things are, and they know that they're slightly different, but when you look at it, you think there's no reason for us to really use one over the other. It's the same. In fact, the density matrix is a bit more complicated, so why would I really even ever do it? So the reason for that is, so for the people who haven't done quantum mechanics, density matrices and state vectors are just two different ways of describing a quantum state, right? But the density matrix is considered the complete version, and I'll illustrate the reason for that. The state vector, you can't describe all of quantum mechanics with only the state vector formalism. So the reason for that is that we require, logically speaking, we would want that our physical theories satisfy a property known as convexity. And convexity is essentially just the, in simple terms, let me illustrate with an example, right? So let's say I have a machine here which can prepare a state, either 0, first flip a coin, I get heads or tails, and depending on that I press a button and it gives me 0 or 1, correct? So the state here is a convex combination. Convex combination just means that the coefficients add up to 1 because we're taking half and half. But it's essentially a probabilistic mixture. Convex combinations are probabilistic mixtures, right? And in real life, there will always be a scenario where potentially you don't know about all of the information about a given system. Like if I handed you a system from this experiment that I've just described to you, you wouldn't really know if it's a 0 or 1. You would know that it's a 0 with a 50% probability or a 1 with a 50% probability, right? So it's in either one of those states. It's in a mixture of those states. It's in a probabilistic mixture of those states. And there's nothing quantum about that. Then you can create such classical states as well. And in general, we would require any physical theory to satisfy these principles. Because it logically makes sense. There are going to be instances in life when you don't know the specifics of an experiment. You've just been given a state, in which case you can't reduce any further. Right? So the convexity is a very natural property that we must demand from our states. Could you just go to the next slide? These are two of the other postulates. So one of the postulates of quantum mechanics is the fact that the composite system of a particular state lives in the, or like is described as in the space that is defined by the tensor space of the individual subsystems, right? So here I'm not really explaining how you get the connection, but the fundamental reason why that shows up, why a composite system is a tensor product of two systems, is something called the no signaling condition. And the no signaling condition is just a no faster than light communication condition, right? So it's just relativity, and more importantly, again, this is an informational principle. This is talking about the amount of communication that you can do, or the speed of communication that you can do, the information that you can exchange with people, right? So this is another informational principle, and if you just follow this down a couple of steps, do the math, what you find out that in any physical theory, composite systems need to be described by tensor products. They need to be described in state spaces that are tensor products of the individual systems, right? So that is a statement in quantum mechanics, and you can derive it completely from informational principles, that is the low signaling theory. Alright, that's a direct consequence of that. Similarly, measurements. Measurements are just so let's say in any physical theory, you have a state and you're going to perform a measurement. So what do you want to require out of your measurement? Like if you're trying to mathematically model your theory, what do you want to require out of your measurement? What you want to require is, in general, any experiment is going to be probabilistic. Deterministic experiments are just special cases of probabilistic experiments with where one event happens to probability one, right? So in general, the result of an experiment is a probability distribution, and what you want is, in your theory, any valid measurement, if it interacts, and using these conditions, actually, you can define like the set of measurements in any physical theory. Once you define the set of states. So this is actually a more deeper concept, a concept of duals, that measurements and states, like how you might be familiar with in quantum mechanics, where you can't just treat measurement like a passive activity. It just so happens that classical mechanics is a special case, but in general, in physical theories, measurements are duals of states. They are essentially just counterparts to states. And that is the reason why once you define states, all these consistency conditions automatically give you the set of all possible measurements, because they're duals. So could you just go to the next slide? So now those were the three principles that I was able to deliver here in a very straightforward manner from completely informational principles. But these are a couple of questions that still remain ad hoc to this day in the academic research. So essentially, if you were to just reformulate the original quantum mechanical statement for density matrices, it is just two conditions. It's positivity, trace one of course, but positivity and convexity. Convexity we've already obtained from more general principles. So positivity is for now ad hoc principle that we don't really know how to explain using informational principles. But once you apply that ad hoc postulate, and you just look at your state space, what you observe is that for a qubit, as some of you might know, the most general state space is a Bloch's qubit. So you can essentially, a qubit is equivalent to a geometrical system that is a unit sphere. So the different qubit states are just points within the unit sphere, right? And that the positivity condition just gives us that. And like I said before, once you have states, because measurements are duals of states, you essentially, that just specifies your set of measurements. It's just a computation, and sufficiently you get the measurements that quantum mechanics in your standard postulates, the way they're presented, you get the same set of measurements when you follow through with these arguments. So this is like just like this is like halfway the journey to completely explaining quantum mechanics using physical and using principles that appeal to base logic rather than principles that specify complicated mathematical structures that one needs to be savvy at math to be aware of or to know, right? We want to construct quantum mechanics in a way that you need to know the math. You just want to see the logic and you want to understand it, right? So, can you go ahead? So, closely related to this, I mean, we're now moving ahead from the topic of the postulates, but now we're going to look at the question of what is information. So, how would you define information? Is this even something physical, or is it just something that we construct to like make sense of the observations around us? Like how, like when somebody observes an event, does he gain information? So is the information getting transferred from a system to another system? What's happening? Where is the information going? And what's really happening, right? So the question to these is actually like answered mathematically actually is surprisingly going to be the major player here behind basically formalizing information into like a mathematical quantity, where we will use entropy to put some quantifiers to our claims here, right, about information and whatnot, right? So, but before that, I'll just address the question of when one observes an event, does he gain information? If so, where does it come from? And if he is gaining information, how much information is gaining, right? So, my favorite example to illustrate this point is, if I told you right now that it was raining in Cherrapunji, you probably wouldn't be that surprised. But if I told you right now it was raining in the Sahara Desert, it was pouring, you'd be really surprised because that's a very uncommon event. So the fact that you got to know the information about the system, the fact that it's raining in Sahara Desert is such a low probability event and it occurred and you observed it, that is our way of saying that the amount of information in that event is very high. And the reason for that is because, again, so in this case, observe how essentially lower probability events, less likely events, when they occur, you gain more information versus when an event that is anyways likely to happen, if that occurs, that means you haven't really gained all that much information. Alright? So, what is informational entropy? So, informational entropy is, it is defined very much so with inspiration from thermodynamic entropy. It very much so still follows this concept of disorder. It's about this concept of disorder. But I'll just relate this back to the previous example, right? So in the previous example, the likelihood of a particular event happening, in the case, let's say in Cherrapunji, let's talk about the rain in Cherrapunji, the probability distribution. Let's just call that 99:1, right? So in that case, we call that a low entropy distribution. The reason for that is because the events that are happening are most likely going to happen in, like, one of the events is going to happen. And the event that is supposed to happen 0.99% of the time, 0.99 times, that's going to be the event that happens so often that really is, if you think about it from the perspective of disorder, that system's not that disordered. Most of the times it's actually giving you like an even value and even output, right? So it's a more uniform system versus, let's say, there's a system that's a 50-50, right? So if it's a 50-50, then really what is happening, it's completely random. It's as random as it can get, right? And so that it's as disordered as it can get, and that's how information experiment. So you can also say that informational entropy is the property of an experiment, and it has a particular mathematical form, and there are particular reasons for it. But the key insight here is this last line that I was trying to illustrate with the example. That with an increase in randomness, we say that the system has higher entropy, and the way we think about that is by thinking of the probability distribution and how spread it is essentially. More spread distributions have higher entropy, and distributions of the spike have lower. Oh, okay. We'll get back to this, but I prepared a little bit more of a lecture, but it requires some understanding of quantum mechanics. So I'll maybe just raise of hands for people who know some very basic quantum mechanics. It's some pretty exciting stuff, unlike this stuff, which is pretty fundamental. You're probably not going to use it, most of you. But if people know quantum mechanics, I could maybe show you some of the more exciting stuff as well. So can I just have a show of hands? So it's terrible. This state is terrible. So this is one. Some of you might have heard of it. We go by the name quantum teleportation, entanglement swapping, which is probably something that a lot of people don't know about. And QPD, I'll just quickly demonstrate the BB84 protocol. For those who know quantum mechanics, it's going to be pretty straightforward to follow. So quantum teleportation and entanglement swapping are actually very related concepts. and they're almost the same. I actually like to think of entanglement swapping as entanglement teleportation also. You can think of it like that. So I think they work on the same principle. So quantum teleportation is this really cool, this really unique phenomenon that you cannot observe in that you cannot observe in classical mechanics. But I'll just quickly describe the scenario to you, and then when I present the result, it should be pretty mind blowing. Alright, A and B are two Alice and Bob. They are two people who want to. So their goal is that Alice here has this quantum state S0. Quantum state coming from the source S0. Alright? And Alice wants to actually send this to Bob, and what they have, the resources they have available to themselves to perform this task are Alice has access to Bell basis measurement, and they both share joint 2-qubit state. Alright? And the mathematical results I won't work out, but I'll just write the equations, the first equation to begin with, and then I'll write out the result, and then I'll explain. Alright? So the first equation here for S0 for a qubit state, it's for any qubit state, it's going to be this. And the state that we're going to consider shared between A and B is going to be the Maxwellian entangled state. So it's going to be, it could be any one of the Maxwellian entangled states, but I have chosen this for now. Right? This is our composite state. And what you're going to find, one second, I have the calculation here. Fine. We're going to call this state, we're just going to I'm just going to rewrite the same exact state as phi plus, which is the standard notation. Right? This is for A, and this is shared between A and B. Right? And if you just rewrite this state, what you'll find is that when you want to write it grouped in terms of A and B, when you change the grouping from A to A and AB to A and B, what you find is that the resultant state is actually this. And rather than writing the full equation here, I'm just going to again just ask you guys to just observe one thing. So if I take my original state alpha 0 and beta 1 and then just apply the x operator on it, what I'll end up getting is alpha 0 minus beta 1. So for the sake of keeping the notation a bit concise, I'm just going to again rewrite this as psi is the one party state of A, and phi plus is the Maxwellian entangled state shared between A and B, and then we choose the groupings that we have is x, y, and z are all unitary operators. So this times an operator, this times a state is another state. And so what you observe here is that now, since I said A is going to perform measurement on a well-state basis, so let's say A performs a measurement and he obtains 5+. What happens to the state? It collapses, right? The superposition collapses, and you get a 5+, and it's going to project over this 5+ term. So what you're left with after projecting over the 5+ measurement at A, you're left with the state psi at B. You see, the state delta. The state psi was at A. This is just the math. The point is that A did a well-state measurement, right? And this state got shifted into this position. Alright? So that's teleportation. And I'll just quickly talk about the other cases here. So the other case is that A can measure and maybe he got a 5-. I'm gonna work with 3 parties, right? I'm gonna work with 3 parties. I could do it with 2 parties also, and that would be more equivalent to the application scenario, but I find that this is a better example. So now I have Alice, Bob, and Charlie, 3 people. Alice and Bob share a state, so if they share a quantum state, they can share entanglement. Bob and Charlie also share a state. They're about 2 qubit states to know, but in general they could be entanglement states. But for the calculations that I'll be going ahead with, I'm just going to use 2 qubit states. So Alice and Bob share one maximally entangled 2 qubit state. Bob and Charlie share one maximally entangled 2 qubit state. Now, Bob and Alice, Alice and Charlie, for some particular reason they want to perform quantum cryptography, which as you'll see later requires parties to share an entangled state. Alice and Charlie want to actually share an entangled state. But in this case, obviously they're not. Alice is sharing one with Bob, and Bob is sharing one with Charlie, and they're both individually sharing an entangled state with Bob, but they're not really sharing an entangled state with each other. So, entanglement swapping is going to be very similar to quantum teleportation, and what Bob is going to do here is Bob is going to measure in the well-state basis. And I mean, I'll write down the math and it'll work out, but what you see is that the resultant of that is going to be that the post-measurement state shared between A and C is going to be entangled. So I'll just write down the math. So I'm again just going to take 5+, which is 0, 0 plus 1, 1 over 2 as the maximum entangled state. So I have 5+. But again, this 5+ is shared between A and B, and this 5+ is shared between B and C. Right? But now we want to write states such that they are BB and AC, because we want to look at what A and C are sharing. That's what we're interested in. We want to somehow create a protocol where A and C are sharing the maximum entangled state. So I'm going to regroup my states like this, and when I do that, what you'll observe is that this is just equal to right, both of them. So they both each can make a choice to measure in either X or Z. Alright? The way they're going to go ahead with the experiment is they're going to receive the state from the source. They're going to randomly choose 50-50. They're going to flip a coin, whatever. They're going to randomly choose which measurement they want to apply, X or Z. And they're just going to apply it. And then they're going to record the result on a piece of paper. They're just going to write it down. And then you're going to do the run over multiple times, because in general you want to generate an n-digit key. Right? So you're just going to do multiple runs. Each run, same process. You're going to They see the state, flip a coin, perform a particular measurement, note down the results. Alright? So let's just say there are n tracks. Some n tracks. Right? So once they run these n tracks, what Alice and Bob are going to do is Alice and Bob are going to they're going to publicly announce half of the results that they're going to choose randomly. So they're going to say, so like we have a list 10. They're going to say, like Alice is going to say, okay Bob, tell me what you got in your third round. Tell me both what measurement you performed and what this thing and what outcome you got. Because both of these are going to give you one of two outcomes. They're going to be 0 or 1 plus or minus. Right? So Alice is going to do this and they're going to repeat this process for half of these runs. Right? For half of these runs, Alice is going to be like, Bob, what was your result? For this, what measurement did you choose and what result did you get? Right? And using that half that they publicly announce, what they can do is, without getting into the nitty gritties, is that they can infer if Eve has tapped their system or not. Right? So if Eve has not tapped their system, essentially they're going to have a matching success. Alright? Because this is the entangled states, right? And if A measures in X and B measures in X, then they're both guaranteed to get either a 0, 0 or a 1, 1. Then it's perfect correlation, obviously. And similarly in this case, versus if they measure in different indices, X and Z, we expect there to be absolutely no correlation. There's supposed to be no correlation. So essentially, what A and B are going to do is they're going to announce these results of half of these runs, and they're going to analyze. They're going to analyze, are we getting perfect correlations when we both measured X? Are we getting perfect correlations when we both measured Z? Are we getting completely uncorrelated systems when we're measuring X and Z? So if they are, that means that Eve has not tampered with it. But in the case like Eve has tampered with it, your state is not really going to remain this. It's going to undergo some sort of evolution that in general in quantum mechanics you do